In this lecture, we'll discuss the working or operation and construction of SR non-gated NAND latch. We can simply called NAND latch also. Okay, so this is the logic diagram. Here we need two NAND gates, two input NAND gates. One of the input of this NAND gate is connected to S, and one of the input of this NAND gate, below NAND gate, connected to R. And this NAND gate output is Q, this NAND gate output is Q bar. This Q we are taking and connecting here, and this Q bar we are connecting here. So this is called cross coupled connection. So this is the construction of a NAND latch. Now we'll see the working. So generally this is the truth table. How we got this truth table I will explain very detailed. Okay, first we'll see the truth table format. So there are two inputs, so four combinations will come 0 0 0 1 1 0 1, and there are two outputs. I listed two outputs. So for 0 0 I am getting 1 1, and for 0 1 I am getting 1 0. For 1 0 I am getting 0 1. For 1 1 I am getting 0 1 only. Okay. So here this is the state or state name or condition name. So whenever both are 1 1 output, both are 1 1 are same, that is we consider as invalid condition, because both outputs should be complementary. Okay, that is the condition. So it is violated that condition. That's why it is invalid or not used condition. This is not useful as memory, because ultimately this latch is for storage. Okay. So this condition we treat as set. Set means whenever, so these three conditions are called valid conditions because both are complementary. See here. Okay. These three satisfied the condition of complementary. So these three we consider as valid conditions and memory conditions. Okay. So in this condition I got 1 0. Whenever we got 1 Q, that we consider as 1 is stored. 1 means set. Okay. But why we are not considering Q bar? This Q bar is just a complemented version of this one. This is same as this one, just it is in the complemented version. Both are same. That's why we are considering only one. Okay. So here in the third condition 0 1. Now 0 stored. So this is we called reset. 0 means reset. Okay. Then next again 0 1. So previously 0 1, now also 0 1. It is maintaining as previous. So whenever it is maintained as previous, then we called hold or latch or no change. Okay, right. But out of four combinations, I told this we don't use. These three are memory. But out of these three, these two are same. That's why you can neglect one. You can consider this one. So finally, we will consider this set condition and reset condition. In set condition, 1 is storing, reset condition, 0 is storing. Okay. So now we'll see how we are getting these Q bar values, invalid, set or reset to hold, everything we'll see step by step. Okay. Now the first condition, S equal to 0, R equal to 0. See here, I listed that condition, S equal to 0, R equal to 0 is the condition 1. Okay. So here I am applying S0, R0. It means this NAND gate, one of the input is 0, but we don't know other input. Here also one of the input is 0, but here we don't know other input. Even we don't know other input here and here, based on the single input, we can predict the output here. Okay. By using NAND gate definition. What is the NAND gate definition? If any one input is 0, then output become 1. Here also any input 0, output become 1. So here output become 1. Q also become 1, Q bar also become 1. So this is happening in the first condition. Okay. And I told both outputs should be complementary. That is the rule. So it's not following that rule. That's why we call it as invalid or not used condition. Okay. Now we'll see second condition. See what is the second condition? 0, 1. See here, 1, 1 we got for the first condition. Okay. Now 0, 1 second condition we'll see. 0, S0 or 1 is the second condition. But in second condition, I will explain with the different cases. This is the case 1. Okay. But in all cases, this input will be S0 or 1 only. Okay. So here S equal to 0 or equal to 1. And what about these values? I feed back the previous condition values. So previous condition values 1, 1 now output values. So now those 1, 1 came here. Okay. Now what is the output of this gate? If any one input is 0, output 1. Here both are 1s, output is 0. Okay. Right. But we should not write this output immediately in the truth table. Okay. We have to check whether this output is stable output or not. Okay. Stable output means I will keep this 0, 1 input as it is. Then I will feed back these values. When I feed back these values also, again I am getting 1, 0. Then that is the stable output. That stable output we have to write in the truth table as final output. Okay. So that's why in the next case, this is the second condition only, but the second case will feed back this case 1 values. Then we'll check whether it is stable output or not. See here, second condition case 2 also my S0 or 1 only. I feed back the previous values. What are the previous values? Q1. This Q1 will come here. So Q1 came here. And this Q0 will go to top. See, this Q0 went to top. Okay. Now both are zeros, so output is 1. Both are 1s, output is 0. So here we are getting Q1, Q bar 0. Previously what we got? Q1, Q bar 0. So this is the stable output. Now this output is the final output because this is the stable output. We have to take only stable output in the truth table. Okay. And I told out of 2 outputs, we consider only 1 because this is just a complemented version. Both are same only. Okay. And latch is a 1 bit storage element. We just need to store 1 bit. Okay. That's why I'm considering 1. This is called set condition. Set condition. So what we got, see, in the second condition, when I apply 0 and S0 or 1, I got Q1, Q bar 0. That's why set. I am considering Q set. That's why I highlighted. Okay. So we are storing 1 here. Okay. Now we'll see third condition. S1 or 0. Third condition we'll see. In this third condition also, we have to check with the different cases until getting stable output. So this is the condition 3, case 1. S equal to 1 or equal to 0. S equal to 1 or equal to 0. So this is 1 S1, this R 0. What about this 0, 1? Previous outputs. What are the previous output? Q1. That Q1 will come here. So here. And Q bar 0 will come here. Previous Q bar 0. Okay. Right. Now if any one 0, then output 1. If any one 0, output 1. Here both are same. So we should not consider this as invalid. We have to check if I feedback these 1, 1 again, whether output changing or not, that I have to check. But in case condition 1, why I have not feedbacked? Even we do feedback, we will get same. That's why, that is the reason. It means whatever I shown for the condition 1, that is the stable output, final output. Okay. So now we will see case 2 for condition 3. We will feedback these output values, but this input will remain as same, 1, 0 only, S1, S0, R0. Okay. So when I feedback previous case outputs, it will become like this. So both are 1s, output 0. Here at least 1 is 0, so output become 1. Okay. But we don't know whether this output will maintain stable or not. So that's why again we have to check case 3. Okay. So now case 3, again I will in case 3 also I will maintain same S1 or 0. I feedback previous case output. So now I am getting both are 1, so output 0. Both are zeros, output 1. So it is stable, because in case 2 what we got, Q0 Q bar 1. Here also we got Q0 Q bar 1. So this is the stable output. So we have to take it as a final output for condition 3, and we have to note down it in truth table. So for S1 R0, what is the output? Say for S1 R0, Q equal to 0, Q bar equal to 1. So we are storing 0. 0 means reset. I told we are taking only Q. Okay, I told the reason why we are not taking Q bar. Okay, but some other applications, based on the applications, we can take Q bar also. We can neglect Q. For example, in 555 IC timer, I observed there we use RS flip flop. There we take Q bar. So according to the application, we take any one. Okay, here I consider Q. Okay, then we'll see last condition. What is the last condition? 1 1. What is the output of this last condition? We'll see. This condition is the condition 4. Here also we have to take a stable output. For that we have to check different cases. So here the input values are 1 1, and I fed back previous case outputs. So this 1 0 will come here. So now both are 1s means output 0. Any 1 0 output 1. Okay. So now we'll check this output is stable or not. Again we'll feedback. When I feedback, I am getting same. So this is the stable output. I will note down this one. Okay, I will note down this one. We'll go to the truth table. So here 0 1 for 1 1 input 1 1, I got 0 1 Q0 Q bar 1. When I observe this one, this 0 1 we got previously also for condition 3 also. So for condition 3 and for condition 4, we are getting same output. So condition 4 maintaining same output as condition 3. So in sequential circuit, if you are maintaining previous output or same output as previous, then we called hold. That's why this is called hold or latcher. No change. There is no change, it is the same as previous. Okay. So here you may get confused between stable output and hold. Hold means when we compare different conditions, that is hold. Okay, stable means in the same condition. Suppose when I take condition 2, case 1, and condition 2, case 2 itself. In the same condition, when we comparing outputs, that is called stable. But when we compare in different condition, that is called hold. Okay, so this is the working of a NAND latch. SR, non-gated NAND latch. In this lecture, you will see why we consider only one output in latch or flip flop. We know there are two outputs for latch or flip flop, Q, Q bar. Of course, we can name other names also. But out of Q, Q bar, we mostly consider Q. Okay. So, why we consider only one output? That we will discuss. Out of two outputs, why we consider one? And one more thing, why we consider Q only? Why not Q bar? Or do we need to consider only Q always? Okay, that also we'll discuss. So if we observe Q1 Q bar, whatever the output we are getting at Q, it's a complemented version we are getting at Q bar. Okay, so it's almost same, just it is a complemented version. That's why we can take any one. Okay, and mostly we consider Q. But it doesn't mean we always should consider Q. We can consider Q bar also. Suppose if you take a 555 timer IC logic diagram, there we use SR flip flop. So there we are taking a Q bar. Okay, so based on the application or design, whatever we want, we can take. Okay, right. Okay, some of my students asking, sir, whether it is SR latch or RS latch. Okay, so we can call it as SR latch or RS latch. Whatever the first lecture I uploaded, that I named as SR. That is SR NAND, non-gated latch. So here, to clarify you, I taken as RS, non-gated NAND latch. Okay, now we'll see the difference between the two SR and RS. Okay, suppose here first condition I taken like RS, so both input 0 0, here we get invalid. Even when I take SR also, therefore 0 0 we got invalid. Okay, then coming to second one, second condition. In second condition there I did two cases, here also I did two cases to get a stable out. Okay, so here if you observe carefully this first condition, wherever I kept yes, straight to that I kept Q. Wherever I kept R, straight to that I kept Q bar. But in first lecture, S is on top and Q also on the top. Okay. Here and there also, wherever S is there, that straight to that you have to keep Q. Okay, that you can remember. Okay, we are interchanging inputs, so you can you have to interchange outputs also. Okay, that you have to remember. Now, second condition, first case, here I am giving R0 S1. Okay, I will take first condition output as feedback, then I will get to 1 0 Q bar 1 Q 0. Then to know the stable output again, I will apply 0 1 S0 R1 and I will feedback this case 1 outputs, then I am getting stable output. So it means when I apply R equal to 0, S equal to 1, what I am getting? Q 0. Okay, Q 0. So there also in the first lecture in SR, when I take S equal to 1, R equal to 0, what I got? Reset. Q 0. Here also I got same, na? Okay? Right. So, one thing we have to observe, one shortcut. So, when both inputs are different, different means S equal to 0, R equal to 1, R equal to 0, S equal to 1, whether it is a SR latch or RS latch, whatever the R value, that will come to the Q. Whatever the R value, that will come to the Q. But this condition applicable whenever both inputs are different. Okay, right. Next condition, third condition, when R equal to 1, S equal to 0. Here I taken three cases to know the stable output. So here also you can observe, whenever S equal to 0, R equal to 1, we are getting set. In SR also we get set, na? When S equal to 0, R equal to 1. And here also you can observe, inputs are different and you whatever R value, that only coming to the Q. Okay, right. So finally last condition, when both inputs are 1 1, I taken two cases to know the stable output. This is the second case. So whatever the third condition final output, stable output 0 1, that only I am getting in fourth condition second case. So this is called hold. Okay, so this is the explanation about SR and RS. So before seeing this lecture, you have to see first lecture, SR non-gated NAND latch. Then only you can understand this properly. Okay, so in that lecture also see, when inputs are different, whatever the R value, when inputs are different, so this is the condition to final case. When inputs are different, whatever the R value, that only coming to the Q. Okay, so here also straight to yes, there is Q. You have to write like that. So in condition 3, this is the final case. Whatever the R value, that is coming to the Q. Here also yes, and straight to that Q. Okay, right. In this lecture, we'll discuss about SR non-gated NOR latch. Okay, so In this, we need two input NOR gates. Okay. One thing we have to observe comparing to NAND latch. Generally, in NAND latch, straight to the yes we write Q, but here straight to the yes we have to write Q bar. That we have to observe. Okay. Some people assume this inputs as SR or XY also, and outputs as Q bar, or we can name some other names also. Here I named as Q1P. This P is nothing but Q bar here. Okay. So these are the constructional details. Now we'll see the operation step by step. So this is the truth table. Here SR two inputs and we will get 4 combinations. Okay. So here I have not started with 0 0. As I started in SR NAND latch with 0 0. Here I not started with 0 0. Okay. Because the reason is NAND latch will be in invalid state when we apply 0 0. Okay. So if we want to make it valid or useful, we should change any one input. Whenever the inputs are 0 0, even we feedback output many times, it will be it will maintain same output. Okay, we cannot go to valid state from the invalid. Okay, so here in a NOR latch, if we keep this circuit in 1 1, when we apply input 1 1, it will be invalid. Okay, so whenever we want to make it useful, we have to change the input values. Okay, and one more reason, suppose if initially if I apply 0 0 to the NOR latch, what will happen? We don't know second input. Suppose here if I apply 0 0 here, I don't know second input of each gate. Then I cannot predict output. Okay. Because there is no output also at that time to feedback. Okay, so we have to start from 1 1. Okay, so even with 1 1, even there is no second input, we can predict the output based on the NOR gate definition. Because in NOR gate, if any one input is 1, output is 0. Like that we can predict. Okay, and here you can see I taken Q here, Q bar here. Okay, these are the state names. Okay, now we'll see this operation step by step. So initially input both are 1 1 inputs. Okay, output is 0 0. Okay, this is invalid. I told now both outputs should be complementary. Okay, so you have to see this lecture after watching SR NAND, then only you can understand it properly. Then coming to second condition, S equal to 0 or equal to 1. Okay, so here I have started immediately S equal to 0 or equal to 1. Observe this. Okay, now 1 initially in first case I am getting Q bar 1 Q 0. Then when I feedback with the same input maintaining, when I feedback this case 1 outputs, I am getting Q bar 1 Q 0. So it is stable output. So I am taking this as final output. See here what is coming when S 0, Q is 0. When S equal to 0, Q equal to 0. This is called reset because this is my Q. 0 is stored. Okay. And here you have to observe in SR NOR latch, output will be same as S, but in NAND latch, output will be same as R when inputs are different. That you have to observe. Okay. Okay, now we'll see next condition. Third condition. So here my S equal to 1 or equal to 0. When I feed back the previous condition output, I am getting in case 1, 0, 0. So I have to look for stable output. So I again fed back with same input maintaining. Then I got 0, 1. It means Q1, Q bar 0. Then again, in third case, I maintained same inputs and fed back the second case, third condition, second case outputs. Then it is maintaining same. So it is stable output. So I will take this as the final output for condition 3. So when S equal to 1, Q is 1. Q is 1. Okay. When S equal to 1, see, when S equal to 1, Q is 1. So it means 1 is stored. It is called set. Okay, right. Then last condition. Now 0, 0 I am applying. So when I fed back, I got 0, 1. And when I check for stable, I got 0. So this fourth condition output same as third condition. So this is called hold. So when I applying 0, 0, circuit becoming hold. So when we compare NAND and NOR latches, so when we apply 0, 0 in NOR, it is becoming hold, but in NAND it will become invalid. And here when we apply 1, 1, NOR becoming invalid, but NAND become hold. And when we apply S0, NAND becomes set, but it is becoming reset. And NAND become reset when we apply S equal to 1, but this is becoming set. So these we have to observe. Okay, right.
In this lecture we will discuss about active low latch and active high latch. The non-gated NAND latch is called active low latch because if we observe the truth table of this latch is invalid or unused when the inputs S are equal to 0, 0. It means when S are equal to low, this is in invalid condition. To make it useful, valid, we have to change any one input. Okay, so NAND latch, non-gated NAND latch is called a active low latch, and a NOR non-gated latch is called a active high latch. Because if we observe the truth table of NOR, it is invalid when inputs are high, active high, or 1, 1. Okay, so to make it useful, we have to change any one input or both inputs. Okay, in this lecture we'll see the comparison between gated latches and non-gated latches. So this non-gated latches won't contain clock or enable, but gated latches contain clock or enable. Okay, non-gated latches are NAND to NOR. Okay, there is no positive, negative, there is no triggering in non-gated latches. But if we take gated latches, there is SR, D, JKT, and they are positive or negative level triggered. Okay, there is a triggering here. And we use, when we constructing gated latches, we use non-gated latches as latch part. Okay, so both gated and non-gated latches are asynchronous. Because in non-gated latches there is no clock, so there is no timing synchronization, so that's why they are asynchronous. But in gated latches there is a clock, but it will work with the levels, that's why asynchronous. Even there is a clock, asynchronous. Because of working with the levels, there is a change in the output at any instant of the level. Okay, that's why asynchronous. Okay, in this lecture we'll discuss about S bar or bar latch. Here I taken non-gated SR NOR latch and I connected inverter to S, so it became S bar, and I connected inverter to R, it became R bar. That S bar and R bar values going to that NOR latch, non-gated SR NOR latch. Okay, I actually give SR values, they will become invert and they will go to NOR latch. so that I will get output accordingly. And here straight to the S and S bar I have to connect Q bar. That is the construction of NOR latch. And in the symbolic diagram you can see, if I show SR you have to use bubbles, but if I show S bar R bar you no need to use bubbles. Okay. Now we'll see working a truth table. I just taken the truth table of normal SR NOR latch, non-gated. Okay. So this is the truth table. I already uploaded this lecture. You can go through this. After watching this lecture only you have to see this lecture, then only you can understand. Okay. Same here we can see when SR equal to 1 1 circuit becoming invalid, and when SR 0 1 circuit becoming reset, when SR 1 0 circuit becoming set, when both inputs are 0 0 circuit becoming hold. So you have to remember these conditions, then come to this S bar R bar truth table. So here first I take an SR value, so when I apply 0 0 what it will become? S bar R bar 1 1. So when we apply 1 1 to NOR latch, what will happen? Circuit become invalid. So when we apply 1 1, see, go back, when I apply 1 1, see what is the state? Invalid. Okay. Like that when I apply 1 0 SR, then S bar R bar becoming 0 1, so circuit becoming reset. And when I apply 0 1, S bar R bar becoming 1 0, circuit becoming set. So this is the Q value. Okay. When I apply 1 1, finally S bar R bar becoming 0 0, so circuit becoming hold. Okay. This is the operation of S bar R bar latch. In this lecture we will see another way of drawing latch, that is non-gated latch. For example, I take an SR non-gated NAND latch. So this is the logic diagram. This diagram we can draw another way also, that we'll see now. See, this is the diagram. It means I taken one 2 input NAND gate, I given the input S. Okay. And I taken another gate, 2 input NAND gate, I given input R. This gate output I connected to input of this gate, and this gate output I connected input of this gate. So this will become Q, straight to the S Q and straight to the R Q bar. This is the another way of representation. This is also non-gated latch. In this lecture we'll compare non-gated NAND and non-gated NOR latches. Suppose if we take NAND, it need two input NAND gates, and a NOR also need two input NOR gates. Okay, number of gates and number of inputs same, but in NAND we use NAND gates, but in NOR we use NOR gates. Okay, we call NAND is active low latch, but NOR is active high latch. Okay, so when we drawing logic diagram in NAND latch, straight to the S we have to connect Q, but in NOR straight to the S we have to connect Q bar. Okay, suppose if we observe the output in NAND, that Q same as the input R, but in NOR Q will be same as input S. Okay, but in S bar R bar latch, Q become same as S bar. Okay. In this lecture we'll discuss about the order of input combinations that we apply to non-gated latches. For example, I take a non-gated SR NAND latch. So it contains 2 inputs, so we will get to 4 possible input combinations: 0 0, 0 1, 1 0, 1 1. You may get doubt, do I need to start from 0 0? Can I apply 1 1? Like that you may get doubt. Or can I apply some other combination like 0 1 or 1 0? Suppose initially if you apply 1 1, we cannot predict the output because we don't know the second input of each gate, and there is no output at that time. to feedback. So we cannot predict output if we apply 1 1 at the starting. So in that case, we have to apply any of other three combinations, either 0 0, 0 1, 1 0. We can apply any of combinations, because even though we don't know second input and there is no output to feedback, because in these three combinations at least one of the input is 0, so that in NAND gate, if one of the input is 0, output will become 1. Like that we can get the output. So we can apply any of these three combinations. But if we apply 0 0 initially, circuit goes into invalid state, unused state. When we maintaining inputs 0 0, how many times you feedback the output, you will get the same output. Okay, so to make the circuit useful or to come out from the valid state, we have to change any one of the input. So if I apply 0 0, I will change this R value. So that combination is 0 1. Then if I change to another combination 1 0, circuit become reset. Okay, so the point is, here we cannot apply 1 1, but we can apply any other three combinations. If you apply 0 0, it will go to invalid state. To make it useful, you have to change any one of the input. Okay. In this lecture, we will discuss about non-gated latches with unequal delays. Whatever the non-gated latches we discuss, those are without delays or with zero delays. Okay. So whenever the gates has equal delays, the working will be same as without delays. So the non-gated latches working without delays and with equal delays will be same. But when the gates contain unequal delays, the working will be different. Okay. For example, this is the SR non-gated NAND latch. It contains two NAND gates. This gate may have some propagation time, and this gate may have some other propagation time. Okay. For example, this top gate may have 3 nanoseconds, this below gate may have 5 nanoseconds, or this top gate may have 5 nanoseconds, this below gate may have 3 nanoseconds. It means they both may contain different delays, and one can be greater than other, or other can be greater than another. Okay, that is the situation. So in this case, how to analyze the working, that we will see now. Okay, let us discuss first condition. When we apply 0 0, what happening? Suppose with equal delays or without delays, how we doing? When I apply 0 0, I am checking the output of both gates at a time. Okay, but when unequal delays, we should not check like that. What we have to do? Suppose now here I applied 0 0, S0 R0, and the outputs are Q Q bar. Okay, so here I take in this top gate has less delay, so it is speeder than below gate. So whichever the gate is faster or less delay, first we have to take the output of that gate, because it will give the output first than other gate, na? Okay, right. So this is 0. If any input is 0, I will get 1. Okay, this is I am showing in this diagram. Next, in this diagram, this whole all diagrams are for first condition 0 0 only. Okay, so here input 0 0 only. Now we got this Q first, so I will feedback this output now to here. Now if any one input is 0, I will get 1. So Q bar is 1. So this is the difference with unequal delays. So you have to get the output of faster gate first, then you have to feedback that output to another gate input. In that way we have to do. Suppose if this below gate is faster, first I have to predict Q bar, then I have to feedback this Q bar to above gate. Okay, right. So finally with 0 0, I will get q bar 1 1 only, even though I feedback many times. When I am maintaining input 0 0, even though we feedback this outputs many times, we will get same output 1 1 only. So this will be invalid. In without delays case also we will get same invalid only, but here what's the difference? How you taking the output and how you feedbacking, that differs. Okay, we'll see remaining conditions also. Now we'll see second condition, what happening when I apply S0 R1. So when I applying S0 R1, already the existed outputs are 1 1 Q1 Q bar 1. Okay, so here gates have unequal delays, so first what I have to do, I have to feedback the faster gate output. So this Q I have to feedback here. So now they both are 1 1. This gate inputs 1 1. Okay, so that what I will get? I will get 0. But already here Q bar 1 existed. So this Q bar existed output, and now the output I got here. Okay, now here there are two outputs now. So first this existed output I have to feedback to this gate. So I fed back this existed output 1 to here. Okay, now if any one input is 0, then I will get 1. Okay, then again I have to feedback this 0, because this is also output now. When I feedback that 0, now also I am getting 1. So this one I am getting with feedbacking this 0, and this one I am getting when feedbacking this one. Okay, so both are 1 1 means I am getting 1. Okay, suppose now if I feedback this one again to this gate, below gate, I will get 0. Okay, so here I am getting Q1 Q bar 0. Okay, but this output, whether it is stable or not, to know that again I will feedback. Okay, this 1 I fed back here, so I am getting 0. Again this 0 I will feedback to this, I am getting 1. So it is maintaining stable. This will be the final output. When I apply S0 R1, I am getting Q1 Q bar 0. Okay, it is also same as without delays, but here we are feedbacking faster gate output first, then slower gate output later. But in without delays, we will check both outputs at a time, na? We will feedback both outputs at a time, na? Okay, that's the difference. Now we'll see another combination. Now we'll see third combination, S1 R0. Here I am getting Q0 Q bar 1 output. When I check for stability also, same I am getting. It is also like without delays. Okay, now last combination with 1 1 I am getting hold. Okay, so these all combination I checked with unequal delays by assuming upper gate is faster than below gate, and you have to check what happening when upper gate is slower than below gate. Okay, that also you have to check. And finally you may think even with the delays, that also unequal delays, this operation or output is same as without delays only. But sometimes you may get different behavior. Suppose here you are applying 0 0. Okay, and you are getting invalid output. Second I applied 0 1 condition. Okay, suppose second you apply 1 1 condition as second condition. When you apply 1 1, keep upper gate faster, then check the output. And you apply same 1 1, now keep below gate faster, then check the output. In these two conditions you will get different output. Okay, that makes the difference. Okay, right.